Hi, and welcome today to this discussion on Murphy's Laws for Observability. I'm Dave McAllister. I am a senior technical evangelist for Splunk, and I work in the observability group. I'm also an open source geek, a standards wonk, and as you'll find out, I'm willing to talk about any topic at any time. Splunk has this belief that everybody is made up of a million points of data. So let me share a couple with you here. I am owned by 3 cats. I'm used to being ignored. I also spent 10 years as a soccer rep, so I'm used to people disagreeing with me. In fact, I'm pretty sure that on any call, half the people on the field disagreed with anything I said. But now let's talk a little bit about this concept of Murphy's laws. Murphy, a law that's been around for a long time, most of you are probably familiar with. Whatever can go wrong will go wrong. And we tend to live with this. But when we add to it the next phrase, at the worst possible time, which was the first corollary to the Murphy's Law's expansion, we start getting into where we need to take a look at observability. And there are a lot of Murphy's Law's categories here. There's Murphy's technology laws. No battle plan ever survives contact with the enemy. There's technology laws, which basically says logic is a systematic way of coming in to an incorrect answer with absolute confidence. And so on. You can see them on cooking, on cars, on physics, on vacations. There are lots of Murphy's laws that come into play. So when we look at this for the observability space, we start finding that we have the same overlap, that Murphy's laws apply to the way that we look at our systems and our infrastructures in particular with astounding accuracy. So during this talk, you're going to learn a little bit about some of the other Murphy's laws that exist, and maybe we'll give you some ideas on how you can best beat Murphy at his own game. So let's start off. Murphy's law number 1 here. If you perceive that there are 4 possible ways for things to go wrong and get rid of them, a 5th one will promptly develop. And any of the people out there who are SREs or DevOps engineers or work in the IT space can pretty much are probably nodding your heads yes, that this is what actually happens for this. What's happened though to make this more interesting, and we'll cover a little bit, is that we now have more scale, more complexity, and the speed of our needed response has drastically gone up. So kind of what does that mean? So what is this thing called observability? It's the new phrase that lots of people are using it here. And the shorthand viewpoint is it's a quality of the software, the services, the platforms, or the products that let us know how the system thinks it's working inside. It's looking at the variables to let us infer what is happening with our systems. And that inference becomes really important. So observability is really all about the data. The more observable a system is, the easier and faster that we can find out why it's acting the way it's acting and fix it or respond to the changes. In general, you'll hear about 3 classes of data in observability: metrics, traces, and logs. And basically they break down into, did something go wrong? Then the second one is, where did it go wrong? That's under distributed tracing. And then finally, what does the system think went wrong? And that's where we get into logs. So metrics really do answer that question about, do I have a problem? That's where our alerts are generated from. And traces let us take a look at what the user's experience through our system was. And so we can actually see how requests or how messages flow through the system. And this helps us identify what specific pieces of the system are in problematic states for this. And then finally, logs are the ultimate source of truth. Basically, the log tells you what the system thinks and sees what is going on. And so those 3 things really do make up that underlying structure, the pieces that give us this observability, visibility into our applications and into our infrastructures. So leading that is observability law for Murphy number 2. Every problem, every solution creates new problems. And what we've run into is we run into observability. We run into a set of changes that have gone in 2 dimensions. Now, Anybody who's ever taken an algebra class knows that you don't change two variables at one time. You change them at one at a time. But when we start looking at the way that our new applications are evolving, we're seeing a microservices design approach driven by loosely coupled communication platforms, be they service messages, be they APIs, be they straight HTTP calls. At the same point in time, we're seeing cloud environments take over and drive the underlying infrastructures, as well as provide some of the service here that are elastic and ephemeral. In other words, microservices are creating these complex interactions. It's no longer necessarily purely linear code. Failures, therefore, don't repeat. When you go to look at a failure, the infrastructure it's running on may have changed. The service to which you connect could have expanded or contracted and be different. And so therefore, debugging becomes a lot more of a challenge. And at the same point in time, monitoring by itself is not just enough. Just looking and saying, are you alive, is not good enough. So what happens is best described by this Cynefin framework here. Microservices have caused life to become more complicated. At the same point in time, our elastic and ephemeral services have caused things to become a little more chaotic. By taking the two together, we end up with a complex environment. And observability is designed to take advantage and show us what's going on in that complex environment. So we can probe, see what's going on, sense, get information on a basis, a real-time basis here, and respond to it. This is the emergent process that we're seeing. And the emergent process is powered, once again, by those functionality. So now that we've seen that, looks pretty straightforward. We've got to worry about this, we have to worry about that. But Murphy's Law for Observability number 3 tells us absolute truth. You can never run out of things that can go wrong. Flashback to Murphy's Law number 1, where it says if you know 4 things and prevent them, the 5th one will appear. This is, no matter how many times you solve 5, 6, and 7, you are going to continue to have things go wrong. And what this now lets us do is by having this rich source of data about what the application believes is going on, we can start looking at a combination of looking at things we didn't even know could go wrong. So in the past, we've talked about things like known knowns. Is the system alive or dead? Am I running out of memory space? Am I running out of disk space? Is my bandwidth saturated? And these are things we knew to look for. And this was where it took the role of monitoring. The old traditional style of monitoring looked at things, and today even monitoring still tends to look at things that we expect could go wrong and know to watch for. But what happens is that we now have this new category of things that we are not aware of, but we might understand how they go wrong. I.e., we've got a service and the network doesn't connect correctly. We don't know that that's going to happen, but we understand that it could happen. And then we can go all the way down to the unknown unknowns, whereas I'd love to give you an example, but they're unknown. And so it's a little hard to do that. But the loose example is we may have a hacker who we believe could possibly penetrate a system. We don't know when, we don't know where, we don't know what their intents are. So that's an unknown unknown that happens inside of that. And to go step forward then, we step to law number 4. And law number 4 is nothing is as easy as it looks. And that gets us into that complex environment. If you remember when we talked about microservices. So this is an example microservices architecture. It's actually a e-commerce model. There's a checkout service, there's payment service. It's pulling in things from the internet. It's got a cart service for you to store. It's looking up things from the catalog. It's shipping into images. So there are lots of moving pieces. And each of these pieces comes into play in its appropriate order. Now imagine that each of these pieces, they are the services, are connected through some communications mechanism, and that each of those services may be running on one or more Kubernetes nodes or inside of multiple containers that change over time. And so when we look at this, we suddenly start seeing that there's all these different interactions that we now need to be able to monitor for, back to that monitoring word here, and observe their behavior. That's the observability word. So monitoring and observability actually work very closely together to make sure that we get to the right sets of information, no matter how complex our services and environments look like. It is not unusual in production systems to see 100 to, I think the highest I've seen was 700 active services at one time being traced through. The nice thing is that when we go to that tracing aspect, we have the ability to actually follow the request as it goes through the service, noting the underlying structure, what infrastructure it's running on, as well as the behavior that's happening in terms of rate, errors, and duration, or RED capabilities. So our complexity in this particular case is cloud compute and elasticity. How many things are running, where things are running is not necessarily the absolute case. We have ephemeral behavior. As we add in things like AWS Lambdas, serverless functionality here, we have things that come and go in a second. And so we need to be able to deal with those. And finally, we have this concept of drift and skew, which means that since we're working with multiple different pieces of structure, each piece has to keep track of its own time. It is possible for those timestamps to drift over time or be skewed in a direction of a faster or slower communication channel. And so complexity gives us that ability to have the flexibility to do what we want to. Observability gets us to understand what is going on. And that goes to law number 5. Very simply, things get worse under pressure. So what I showed you as a microservices map is pretty straightforward. Now, let's imagine that you're looking at 2,247 active hosts. Each host is running somewhere between 1 to 4 Kubernetes pods. Each pod is running somewhere between 2 to 4 or nodes to pods to containers, and those containers each contain a service. And all of a sudden you start looking at a totally different picture of complexity. Our scale matters. And in fact, our scale goes up by looking at all these different elements. We have namespaces that are scaling. At the same time, we have services that are scaling. We have back-end versus front-end issues. And we have number of ingresses, number of points where data is coming into the system. We have churn, pods coming and going away. We have pods increasing numbers, decreasing numbers. We have all the network structures that are under here. So all of these things allow us to have this scalability, but scale isn't single dimension. Go back to the Cynefin framework here. We have lots of dimensions, and now scalability is actually taking us along that edge of a little bit on the chaotic side so that we have to worry about all these things at one point in time. Observability lets us pull that data together. The problem is that you've got to make sure that you get all of the data, because unknown unknowns mean you don't know which of these pieces you're going to need at any given moment. And that leads me to law number 6. If it's not in the computer, it doesn't exist. And this leads us to some interesting things about what data you bring in, where you retain and how long you retain your data, and honestly, even something as simple as sampling. So observability is a data issue. And quite often you will hear people talk about observability as a data problem. It's not really a data problem. It's the fact that we have to be able to handle the data in intelligent ways to make sense of this. Data is only as useful as you can aggregate it, analyze it, and respond to it. Under analyzation, you can add visualization, which becomes part of that structure for this. But let's take a look at this sampling, this sampling sample. Try that 6 times fast. So the first one is a traditional sampling model. And I'm simply going to go through and I'm going to grab a sample out of these pictures. And this is a number of traces. We're looking for errors that show up here. And I can see that my trace duration in my sampled model is about 1 to 2 seconds. and I've sampled one trace out of the 30 or 40 that is there. This is not unusual. Seeing sample rates for tracing in the 1 out of 100 or 5 out of 100 is not unusual here. But if I take the same series of data and I look at this and keep track of every single thing that's going on, I all of a sudden see that my trace duration is in the 29 to 40 second range. In my world, 3.2 seconds is considered a lost sale. And so you have to be able to wear this. So take a look at this, that all of a sudden, you're not getting the observed data. You're now getting what someone thinks you should observe. Flashback to unknown unknowns. We don't know what could go wrong yet. And so by sampling, we smooth the data out. We have thrown away potentially useful data for solving the unknown unknowns for this. And by the way, we have completely missed the fact that we would have set off an alert that says something's going wrong, your duration has crept up, and you probably have unhappy customers. So 7, because of this, talks about this is availability is a function of time. And this is actually really important. The resolution and speed of your data directly impacts the insights you get. So I mentioned, for instance, serverless and Lambda functions. I haven't looked at the data recently, but if I recall correctly, an AWS Lambda's warm start is about 30 microseconds. And in my world, our average Lambda execution, how long the Lambda stays in place, is about 1.2 seconds. So that if you're pulling data in, and you're pulling data in at whatever range, and you're displaying it every even minute or 5 minutes, all of a sudden, think about how many Lambdas could have come and gone, started, completed, stopped in that point in time. So resolution and the speed at which your data is both ingested and visualized is increasingly important in our instant gratification society. And that leads us to this discussion around accuracy and precision. Quite often you will hear these interchangeably, but they're not. Accuracy means the measure is correct. Precision means it's consistent with all of the other measurements. So think of this in terms of target shooting with arrows. And you shoot 10 arrows, one of them hits the bullseye, and the rest of them are scattered randomly across your target. In fact, in my case, 2 of them missed the target completely for here. I was really accurate once, but precise was not part of my vocabulary. Now, imagine that I've taken the same 10 and I've grouped all 10 in a 2-inch, 5-centimeter circle in the outside ring. I am amazingly precise. Too bad I completely missed the point that was under discussion. I have completely blown the issue. Observability actually depends on both. We have so much volume of data coming in that we have to be consistent with every other measurement. We also need to be absolutely sure that what results we are getting are the results that are intended. And so accuracy and precision both play a major role in our observability space. But aggregation and analysis can actually throw this off. And to take an example of that, let's look at this. And this is a very simple chart. What I've done, once again, is I've measured a set of requests coming in. This is the request metric. And if you're familiar with RAD, radio duration monitoring, this is the R side of this. If I take these 10 things, 1 per second coming in, and I can look at the 10-second average here, I have a 13.9, and my precision, or my 95th percentile, is about 27. If I take the first 5, my 95th percentile is 29. If I take the last 5, my 95th percentile is 19. And if you notice, both of these aggregations completely missed my alarm that was set at 30, even though one of my request rates crossed that boundary. And so, again, aggregation as well as skew can put things in different groups. There's buckets that I was just talking about. Skew can put things in different buckets. They can affect what happens in your accuracy and your precision. And that kind of leads us to the next point, which is that Murphy's Law number 8. If anything cannot go wrong, it will anyway. So the other way of looking at this is you can't ever stop somebody from figuring out how to break your system. They have no intent to break your system probably, but they're going to break it anyway for that. And because of that, as well as the fact that our world has changed drastically going across this, we're now seeing that we have new facets of where we have to take a look at this. So in a rough environment, we have a front-end environment, we have a back-end environment, and we have a collection of users talking to infrastructure that lives sort of somewhere in between this. And now we need to look at the tooling, that's the functionality that underlies our observability piece that lets us take this data and putting it into meaningful aggregations and visualizations. And we start with synthetics. Synthetics is the ability to run a test case or a request that we expect that we know the results for. And so synthetics say, go do this, and I expect that you're going to come back in a certain amount of time. It sets your baselines. As you make changes to your system, you run the same synthetics test, you should get the results that you're looking for. If something goes really haywire in a synthetics role, then you know that you've actually deployed a problematic area here. The problem is that synthetics gives us tests to which we expect results. Users are really clever at giving us results that we don't expect. And that's where we need real user monitoring. So real user monitoring comes in this and lets us look at each user's request individually. In fact, users really only care about sort of 3 things: the request, this specific request, how long it took, and whether it was successful or failed. And if you think about it from that way, then each user needs to be examined separately and take a look at the usability aspects for that. And they can be across multiple devices. They can be sitting on your desktop. They could be on a cell phone. They could be an IoT device connected to a car going through a 1-mile long tunnel, and you're going to suddenly play catch up at the back end for this. And that leads us into endpoint monitoring. How are the users connected to us impacts the user experience? And so we need to be able to monitor for that as well. And of course, we run across multiple environments. We run with third parties, we run with supply chains, we run with virtual machines, containers, Kubernetes, on premises, in clouds, you name it, somebody's got it. And so we need to be able to look at what's going on in the environment in relation to all of those other people. Once we've done that, we move to the back end. And the back end is our traditional monitoring, the dashboards, the graphs that show us what's going on. And graphs are really useful in helping us understand when something fails, but it's actually as useful in a concept called safety 2, showing us that everything is actually working correctly. And so dashboards are both a comfort as well as the first line of defense, if you will. We also need application performance monitoring because our users do care about what's going on inside of here. We need to be able to look at the events and logs. We need to look at the infrastructure. And if something goes wrong, we need to tell somebody that it went wrong and tell them the right person at the right time. Underlying all of this is that network bandwidth, network communication, both inside of our applications as well as out to the user and through all of the infrastructure. So Murphy's Law number 9. Whenever you set out to do something, something else is going to have to be done first. I've built a lot of classic cars in my lifetime. I can almost guarantee that I will have to make at least one trip to find something that I needed before I get started to do what I want. And what's happened is that our world has evolved from what we used to call observability 1, where we collected those 3 classes of data separately. Logs came into 1 and were visualized, traces, as well as metrics, and each one was different. And we ran into the problem of correlating across that line at the bottom. Now we've moved into the world of open telemetry. And what this does is lets us collect all of that data at the same point. So our data remains correlated. This gives us the ability to actually enrich our data, unskew it, if you will, in many ways, as well as correlate across the things. So if an alert comes in, we can see what the infrastructure was doing at that time, as well as what the user was doing at that time, as well as what the application was doing at that time. And so correlation from this 1 to 2 issue is really important. And that's fortunately becoming more and more the case with what's known as OpenTelemetry. So OpenTelemetry is a project that was the unification of OpenTracing, a cloud-native computing foundation project, and OpenCensus, which was an open source tracing project led by Google, that now is OpenTelemetry. And we're all backing OpenTelemetry. So OpenTelemetry is the next major version of these. It's now rapidly becoming the widespread de facto standard for doing this. And I'm pleased to say that we are actively involved and contributing heavily to both the development and the deployment of OpenTelemetry. Now, along with the laws, I do want to cover the fact that there is at least one axiom that I think is actually really important, and that's called the Ashley Perry statistical axiom. I have a degree in statistics. I do know how to lie for a living for this, but numbers are tools, not rules. So what the number shows you is something that you need to interpret and act upon. The number is just a number. So our metrics are just numbers. But what you really want to do is want to know what's coming. And we tend to use our numbers as trend lines to indicate what's coming. Humans, by the way, are really good at outguessing in short blocks. It's really easy for me to say, I've seen this happen for the last hour. In the next second, it's likely to be blah. So, but prediction is only as good as that precision and accuracy. Keep in mind, we talked about this. If your precision is terrible, then it's hard to predict because you're all over the place. There's no clear indications. If your precision is precise and your accuracy is bad, then you're going to get the wrong results. But here we can start looking at sort of the comparison between what has happened to what will possibly happen. And we look at things like historic. Did this happen last Wednesday between 2 and 3 o'clock and has happened every Wednesday between 2 and 3 o'clock? Then it's probably something that probably should be expected. Maybe an alert on it, but it's not something that I need to say is, oh my God, look what's gone wrong for here. Sudden change. All of a sudden, my request rate has dropped from 100 to 1. Something is probably causing a problem. And so we need to look at what those things are. If our trend is stationary, you're used to drawing a perfectly straight line across here, you're pretty comfortable predicting that the straight line will continue. And the last one I'm going to cover is really this last bullet, is Hill's commentaries. Everything I've talked about is really important. But if it doesn't matter, it doesn't matter. But what observability has taught us is that it doesn't matter until it does. So you plan your observability to find out things that didn't matter or didn't get known about, but now they matter. And observability lets you backtrack and actually understand what their underlying causes were. And finally, just because Murphy's Law number 10, all's well that ends for that. And with that, let me thank you for joining me today for this discussion on Murphy's Laws. You can see my LinkedIn information. Feel free to contact me with questions or comments, or if you have a law and how it applies that you would like me to take a look at, I would love to do that. With this, also let me point out that there's a survey. And if you've enjoyed my session, no matter what, fill out the survey so we can understand how we can get the information you need to you at the right time. Thanks for joining me today.